Sorry?
Which house was your favorite?
I forgot the houses that I think.
Johnny, Targaryen, and then Lannisters, Baratheons, Greyjoy.
Targaryens. For a moment, it was Gryffindor, but that's something else I think. Wait, I forgot those as well. Hufflepuff and Gryffindor and Ravenclaw and Slytherin, right? All right. So, as I just mentioned earlier, Askyoche, I'll be wrapping up this particle physics topic. We have covered more or less everything. There's some strange small parts that show up sometimes. ওগুলো আমি আলাদা করে রাখছি। ওগুলো এখন একটু discuss করব. So I'll go through the whole idea of quarks and leptons one more time, and then key type of question জিজ্ঞেস করে ওগুলো দেখবো because there's some provided here. We'll practice those. আমাদের হচ্ছে একটা জিনিস বলে রাখি question paper করবো আমরা, but I'll do like one set first. Like, you know, paper 1, paper 2, paper 1, paper 2 variants of 2019, right? I think maybe May 2019. তারপর যেটা করব, I'll do all the review questions of waves and electricity. কারণ waves and electricity problemটা হচ্ছে কি, we didn't really do many questions. So ওগুলো question করাটা most important. If there was any chapter that I would say that you have to do the questions, it's just waves and electricity. We spend way too much time হচ্ছে mechanics, you know, but eventually দেখবা যে ওইটা যতই পারো, it's the waves and electricity that matter more, right? Unfortunately, the way the syllabus is designed, and we don't really have time now. So তার জন্য আমি যেটা করবো, রিভিউ কোয়েশ্চেন সব করবো, and ওই যে এমসিকিউ অনেকগুলো দেওয়া আছে like 100 and 110, right? ওগুলা পড়ে আসবো, ওগুলা থেকে যেগুলোতে প্রবলেম আছে ওগুলো আমরা ডিসকাস করবো, okay? So waves and electricity আলাদা করে I'll, like, you know, do a recap. And yes, then we'll go back to our question papers again. But তার আগে I'll just do one set, যে কোনো একটা year পুরোটা করবো. Right, so these are your quarks here. কি লাগবে তোমাদের একটু বলে নিই দাঁড়াও। This box, random at the box, but এখান থেকে কিছু জিনিস লাগবে আমাদের. So yeah, I'll be going through that in a bit. So I'll first do a recap of what we did so far. Art. Right. So let's look at what this is. The model that you see here is called the JJ Thomson model. Okay. So the model the first one you remember. So what's the structure? It's a wrong model. It's something that they ask, like, you know, what were the JJ movements in the other model? So you have one model is, and then also you need the other models, right? It's pretty different. So it's basically JJ model, which is that or the model. Essentially, is that the wall that you see here is like a permeable material, right? And the charge of this positive, right? The wall itself, the red color part. And inside that wall, at different locations, you can spread out key exists for it, electrons, right? It eventually came back again. Modern day atomic structure. This is a place where the electrons are all known as the electron cloud. There's this term called the electron cloud. Have you done electron cloud? It's basically, do you know that electron can pinpoint করা যায় না? Cannot. It's moving everywhere.
It doesn't stay still.
Acha, okay. Acha. ঠিক আছে, ব্যাপার না। So this is the plum pudding model, and then after that we came across the one that's sorry, this is the one. এখানে দেখবা যে vibrate করতে থাকে, because we figured out electrons have energy, but we didn't know like how the energy manifested, right? So we eventually found out the electrons were actually vibrating within the positive structure. Wrong shot, by the way, right? But there are some things that were right. For example, was the total charge 0, right? Which is bigger, proton, which is smaller, electron, and how are the electrons placed? They were scattered around, right? These are all right. And also the electrons had what in them? Energy. So the energy day vibration show kora hocche. But then after that came the model that we know now. It's called the Rutherford model. A Rutherford model এটা হচ্ছে is called a planetary model. এই যে নিচে লেখা আছে the planetary model, right? A planetary model হচ্ছে একটা mistake ছিল that we thought it was entirely 3-dimension. Do you see how it's 3D, right? And do you see how the electrons are just randomly moving around like planets, right? So this is the one we are learning, by the way. Or it's a wrong version. But what is better here compared to the J.J. Thomson model or the plum pudding model? What's an improvement here? Sorry. আচ্ছা, electronটা কিন্তু এখানেও wrong. So electronটা কিন্তু right না. But what's right about this model? Yeah, the nucleus. This is the first time we ever came across the word nucleus of an atom, and the nucleus contains protons and neutrons. It's very small, very dense, very massive, right? We idea was right here. So from the J.J. Thomson model, the plum pudding model থেকে এই মডেলের হচ্ছে change or improvement was that we discovered the nucleus of an atom, and that the atom is not a ball. It's basically a very small part in the nucleus, and the surrounding region where the electron is usually empty. That's why 99.9% of the particles just went straight through, right? But this is wrong actually. কারণ এখানে হচ্ছে wrong কেমনে বলছি তোমাদেরকে আমরা হচ্ছে eventually বের করি that this version এটা 1911 হচ্ছে বের করা হয় এই মডেলটা, right? Within a couple of years we found that this is wrong. And what's wrong in this model? Not the nucleus. To this date, right? Nucleus is perfect. That's why we learned the Rutherford model. What's the problem here though? The electrons. And to this date, electrons এখনো বোঝা হয় না। So তোমরা যেগুলা শিখে আসতেছো বা শিখতেছো বা শিখবা, there are all certain types of assumptions. They work in certain places very well, তার জন্য করা হয়। I'll give you example. তোমরা ionic bonds and covalent bonds all over যখন শিখছিলা, you learn about orbitals and you learn 288 configuration, right? But then you know that's not right. And then A level says you have to go to the SPDF because that made more sense A levels. But then once you go to university, you'll realize that the SPDF is not working. There's this Pauli's expulsion theory. You have to go to the Bohr's theory. There's this Heisenberg principle of uncertainty. And then eventually Schrodinger. Different models চলে আসছে, different models কখন use করতে হয়, different types of scenarios, right? So I'll just give you a quick explanation of what this is. This is 1913, I think. This is the right model of an atom, and right model for A level purpose. Amra A2 থেকে we learn this model in physics. Chemistry তে শিখানো হয় না মনে হয়. So এখানে হচ্ছে the change that Bohr came up with was that the atom was actually flat. Remember the previous one was 3D, right? It was flat, and he came up with this concept that there are these shells. Shell বলি না আমরা? ওই shells গুলো হচ্ছে is the Niels Bohr's model where the electrons were fixed energy levels থাকে, and ওদেরকে remove করতে একটা certain amount of energy provide করতে হয়, যেটাকে বলা হয় ionization energy, right? So এগুলো সব Niels Bohr model এর উপরে base করা, and I think within another year this was proven to be wrong because turns out Eta is the right model, and I know a lot of students actually know this, but they don't know it's 3D. এই শেপটা অনেকে ড্র করে, লাইক এরকম সার্কেল থেকে এরকম একটা থাকে, সবাই ভাবে যে maybe this is how the electron is moving, like an oval, right? It's not oval actually. It's actually a circle, but you're looking at it from a different angle. ওই তার জন্য angle থেকে দেখলে it looks like হচ্ছে skewed at the circle. Okay, even like when I did my, I think chemistry ছিল আমাদের, I used to think it's an oval path. Eventually I understood that it's not really oval. ওই 3D কোনো সময় acknowledge করা হতো না, so তার জন্য দেখলে মনে হচ্ছিল it's oval, but do you know perspective, like a rectangle হচ্ছে trapezium হয়ে যায় when you look from the front, because পিছের দিকে narrow হয়ে যায়, right? Circles আমরা all over মনে আছে magnetism এর right hand rule এর জন্য circle গুলো top view থেকে দেখতে হতো, because ওই যে concentric circles সামনে থেকে দেখলে what do they look like? Oval, right? So this is the problem. দেখো এই যে এখান থেকে দেখলে they look very strange, right? But do you see that they're actually 3 dimension? এই যে এদিকে এদিকে একটা অ্যাক্সেসে যাচ্ছে, এদিকে একটা অ্যাক্সেসে যাচ্ছে, ওদিকে একটা অ্যাক্সেসে যাচ্ছে, রাইট? এটা ইজ ইউজ ইন সাম বন্ডিং সিনারিও, সবসময় লাগে না। এটা 1916 এ, and then this is the part that ruined it, actually, unfortunately. 10 years later, Schrodinger came along and he said that electrons don't exist, and he said that the electrons can exist, might exist based on how you observe it. So it's based on your observation. So turns out আমরা এটা হচ্ছে A2 তে শিখবো, electrons are actually waves. Okay, they're not particles in an atom, and because they're waves, right, you can't pinpoint them, and that's why we know there's a probability that they're somewhere here, but we can't say they are here. Do you get the difference? Because আমরা যে light থেকে আমার bodyতে light পড়তেছে wave, right? Can you show me the wave? No, right? But is the wave in between the light and me? Yes, right? কোথায়? Everywhere. That's why we draw like a region where the electron may lie. But if it was a ball that's falling towards me, right, wouldn't you be able to locate the ball at a moment, right? Electron is a particle, which means the electron is not a particle. What is it actually? A wave. Okay, electron becomes a particle. Don't get me wrong. You haven't learned anything wrong. When they bond, they become particle, and then they become wave again. Okay, it's called a wave-particle duality. It's the gateway to quantum mechanics. Okay, which we have in A2. Right. আর এরপরে আসছিল হচ্ছে the model that they can দেয় নাই as the uncertainty principle. Okay, so yeah, that's the structure that we saw. So Rutherford modelটা কি হচ্ছে এটা করার জন্য মানে certify করার জন্য couple of scientists physicists did an experiment. Do you guys remember the experiment? Which experiment? কোন experimentে we confirmed that the Rutherford model was valid. Yeah, it's a alpha scattering experiment. Okay, so the alpha scattering experiment looks something like this. So what you do is you're basically firing alpha particles here, right? Do we need to know all the models previously? No, previously just Rutherford পর্যন্ত fine. Bohr and everything is not needed for our syllabus right now. But এখানে দেখো কি হচ্ছে, as the alpha particle goes closer and closer to the nucleus, do you see how it deflects? Right, and that's exactly what we see with the deflection. But do you see that the region, right, where the electrons are, ওখানে কিন্তু alpha particle অত এটা হচ্ছে না, মানে deflect হচ্ছে না, the blue dots, right? Do you know why? Why aren't the alpha particles getting deflected as they move through the electron cloud? No, they still have charge. Right, they should insignificant. Yeah, I'll give you a very simple example. If you take a real car, like actual একটা গাড়ি, and you consider that to be a proton, right? Can you tell me what's a comparable size for an electron? Yeah, exactly. Matchbox গাড়ি গুলো থাকে না? Exactly same ratio. In fact, it's 1:2000 ratio, which is proton or electron ratio, right? So যে একটা toy car যেটা আর একটা real car, its size and mass and everything, their ratio, that's the same. So my question is, an actual car is driving through like a field of Hot Wheels, right? Do you really think that that actual car will face any kind of hindrance? No, right? But it actual car is heavy because this is 4. It's an alpha particle. So imagine a truck that's going through a field of Hot Wheels, right? That's, absolutely no deflection whatsoever because of the electrons. So the correct answer is because they're very, very insignificant in size to cause any deflection. Okay, so yeah, this is it. Now আমি যদি একদম straight করে aim করি একদম at the target, right? দেখো কি হয়, do you see it goes back? So the idea is that if you can hit the target straight একদম মাঝখানে, which will not happen very often, right? Because the nucleus and the target is what, extremely small. তার জন্য you'll find that 1 in a billion or this crazy number, 1 in a trillion particle will only come back, but it does come back, which means that it collided, right? So that's how we know the structure of the atom. And before I move on, this is the yeah, possible. এটা যদি দেখো, this is like a good representation. This is basically the experiment, whole foil experiment. Do you see কোন দিকে যাচ্ছে ওরা? So আমাদের original anticipation and expectation কি ছিল? All the particles will go where? straight, right? But দেখো এখানে straight যাচ্ছে, majority of them. Once in a while, if you're lucky, you'll see that one goes like really side আচ্ছা এগুলা slight deflection পাচ্ছি কিন্তু যে that went slight. So these are small deflections এগুলা দেখতেছো এখানে. Small deflections কেন হয়? Right, so small deflections take place because of collision or repulsion. Okay, so small deflections are because of the interaction between the nucleus charge and your charge, right? And large deflection, যেটা খুবই unlikely দেখার জন্য এখানে but হয় যে পুরোপুরি পিছে চলে যাবে like that one, right? ওটা কখন হয়? When it actually hit the nucleus, otherwise পিছে আসার reason নাই. Okay, so yeah, this is the model that we did last class. Are clear about that? Okay, so I'll just show one more version of this. Right. Yeah, why do we use gold? Gold to create the thinnest layer of atoms possible. And gold is extremely malleable, number one. And number two, gold atoms are what in size? Very big in size. So if you put these two into a combination, you'll have like the single like, you know, least number of atoms in a layer possible. Okay. আচ্ছা একটু এদিকে দেখো কি হচ্ছে. This is the Plum-Pudding model. No, Plum-Pudding model. Yep. So yeah, Plum-Pudding model alpha particle পাঠালে কি expectation ছিল? This, right? What will they do? Just pass straight through, right? This is the Plum-Pudding model. And the Rutherford model যেটা আমরা notice করছি is that as you send it, it can actually be difficult, but see if you can see them. They're traced. Do you see how they're moving around? There's a deflection হচ্ছে left, right, যাচ্ছে. So এই যে এখানে যেসব particles গুলো, most of them কোথায় যাচ্ছে? Straight, right? But once in a while, won't you find like one go left and right very drastically? Those are small deflection. There goes the one. That's the one went back, right? That's because it hit the nucleus, right? So yeah, this is it. আমাদের একটা question জিজ্ঞেস করছে একটা ইয়ারে, দেখি তোমরা figure out করতে পারো নাকি. What if the alpha particles have low energy, right? Like there's a way you can actually control their energy. So if you can make alpha particles of lower energy, right? How do deflections differ? Would they be more deflection, like larger deflections or fewer deflection? More. Few. I'm not talking about the number of deflection, I'm talking about the amount of deflection. Yeah, the degree. So you think that with low energy, the degree will be less. And you think more. Anyone else? Less. Same. Acha. Question কি বুঝছো? আমার যদি alpha particles গুলো slower হতো, the deflections that would take place, right? Would they be more prominent or less observable? If the energy of my alpha particles was lower, less angle, okay. So the correct answer is it's going to be way more prominent. And the reason behind that is when something goes very fast, right, it doesn't really get time to interact with the repulsion. So it just barely goes by. But when something's coming very slow, only time to slow down. So only easily deflect. I'll show you with an example here. I'll reduce my energy there. See what happens. Do you see they're all going sideways motamoti? Do you see the amount of deflection is greater now, right? Can because a version I think are easier. Do you see how they're barely making it next to it? Can because eto slow that repulsion eto beshi hoy that they go back, right? Whereas if I make them very fast, see, they have enough energy to like go past them almost, right? That the next deflection gulo কম হচ্ছে. You get my point? Okay, fine. Right, so let's get back to our topic. আমাদের এখানে কিছু নোটস দিব তোমাদেরকে, but before that question থাকলে আমাকে বলতে পারো. There's some questions online, let me answer those. Protons and neutrons are baryons, correct? Shouldn't Plum-Pudding model also cause deflection because the pudding is positively charged and the alpha particle is also positively charged? It's uniformly positively charged. So when you have a uniform distribution of charge, right, what's the deflection? Nothing. Uniform মানে বুঝছো তো, the amount of positive charge is the same everywhere.
So there's no net positive charge. So তুমি যখন মাঝখান দিয়ে যাচ্ছ, এই সাইড থেকে তোমাকে লেফটে ধাক্কা দিচ্ছে, এই সাইড থেকে তোমাকে রাইটে ধাক্কা দিচ্ছে. So what do you end up doing? Going straight through, right? So that's why the plum pudding doesn't really cause any deflection. Right, so quick reminder of the particles that we learned last class. So we have the fundamental particles here, which are quarks and leptons. Quarks are particles that are responsible for applying what force? Strong nuclear force. And leptons are responsible for applying what force? Weak nuclear force. The quarks are up, down, top, bottom strings charm, right? The leptons are electron, electron neutrino, muon neutrino, tau neutrino, right? And the charges of quarks are +2/3, -1/3, and the charges of leptons are -1 and 0. Okay, but they have a alternate pair out there, which is known as antiparticles, right? Antiparticles are exactly like your particles, with one exception though. The nature of their charge is opposite. মানে এটা positive হলে ওটা negative, বাকি সব same. Even the magnitude of the charge is same. So you জিজ্ঞেস করো what's different about them, and if you say charge, right, তাহলে কিন্তু misleading. কারণ আমার +1 আর -1 কিন্তু 1. So charge কিন্তু same. What is different about the charge? The polarity of the charge, the nature of the charge. So just charge বললে কিন্তু একটু problem. Tell that the nature of charge is different, okay? Mass same, and everything else is same. তারপর হচ্ছে, yeah, basically these are the particles out there. Now quarks can combine, leptons can't combine. Keep that in mind. Okay, leptons কোনো combination হয় না, but quarks can combine, and the combination of quarks is known as hadrons. So when quarks combine, they're called hadrons. Hadrons হচ্ছিল can be of two types, baryons and mesons. Baryons are when quarks combine with what combination? Three quarks. Should they be quark and antiquark, or any three quark? Any quark. So it could be quarks, it could be antiquarks, it could be all three quarks, it could be all three antiquarks. No problem. As long as your charge gives a whole number, that's the requirement. Okay, that's for baryons. And the famous baryons that we have are protons and neutrons. Okay, so proton and neutron, the two baryons that we have are when quarks combine with two to form like a combination. It's called a meson. And two combination we tried this out. Quark সম্ভব হয় না. It has to be a quark and what? Antiquark, technically possible, right? So meson strictly, and this is a very common question so far, is that meson key for a quark and an antiquark. Any quark, any antiquark, but a quark and an antiquark. Okay, right. A baryons need to issue us. If you look up on the internet, you'll find that 5 follow 3 and 5. By 3 combination and 5 combination. 5 combination of possible chilo in theory. It's still now possible in theory, but I think 2001 they actually made a 5 combination quark artificially, and we believe that 5 is possible, but later on it was found that it was fabricated. Their research was completely fake. South Korea and they like, I think one of them apologized and whatnot, but they fabricated it, and for many years we thought 5 is the answer. Like 5 combination is also possible, but energy bhabe 5 stable hoy na. So 5 are hoy na. So eventually now it's concrete that is just 3. Okay, so some old documents above a 5 bolera, which is not actually true. Okay, quark and antiquark combine korle baryon hoy. Quark and antiquark কিন্তু কয়টা? 3টা. Baryon মানে 3টা হইতেই হবে. There's no exception to it. Just quark and antiquark যদি হয় তাহলে it's a meson. Okay. Right, so these are the things that you need to know. A topic to know, I recommend that you read the book. The textbook does it on a topic to know. And there's so many small bits and pieces out there that maybe a table boosters, right? Maybe I might not even bring it up with like us. So boita each chapter and okay. Right, so that is it. Now there's the last thing that I want to show you. I'll give you a small note on what we did so far. So yeah, this is miscellaneous information. Not in your syllabus, not in your book, but in your paper. So it happens sometimes, right? So we say, they'll ask you, when particles interact, right? What are the laws that are conserved during the interaction? So you'll find a lot of questions about alpha particle, alpha particle, you bring them form the theorem, and what is the formula of alpha particle, and theorem the momentum, alpha particle they'll ask you which one is faster. Alpha particle, because the momentum you just say our momentum say level and mass level also right? So we should question it, all of that. What else is there in interaction like that? So there are three things that are conserved in the universe, okay, everywhere. What are those? Momentum, charge, and mass energy. Mass energy at this moment energy ধরে রাখো, but future you'll learn that energy or mass together conserve হয়, কারণ mass and energy interchange করতে পারে. Okay, so we don't have that in our AS, but we have that in A2. So yeah, you have momentum, you have charge and energy. Okay, so that's the conservation law out there. আরেকটা হচ্ছে, there's this quantity that we need to learn called electron volt. I've seen like 2 questions on this in the last I don't know how many years, but we take দেখছিলাম ওরা কি করছিল, ওরা এরকম একটা নাম্বার দিয়েছিল and they ask you to convert this into a unit called an electron volt. So what's an electron volt? So electron volt is just a unit of energy, আর কিছু না, but it makes your numbers that are very small into much more manageable numbers. And the reason behind that is subatomic level energies are always 10 to the power minus 19, minus 21, minus 18, very small numbers, right? Electron volt convert korle, they become a much useful number, like, easy to write. So for example, 1.139 into 10 to the power minus 7 joules, right, is 71.2 electron volt, which is much more easily, readable, right? So how do you convert it? Super easy. You just divide the value in joules, right, with the charge of an electron. So তুমি যদি হচ্ছে EV তে convert করতে চাও from joules, right, just divide the number by the charge of an electron. আর তোমার যদি এইটা থেকে হচ্ছে joules এ যেতে হয়, what would you do? Just multiply. So you just 71.2 কে multiply করবা with the charge of an electron. That's it. That's the process. আমি এখানে লিখে দিয়েছি, joule to EV, divide, EV to joule, multiply. Okay, একবার দুইবার আসছে, so I think জানা উচিত. Does the laws break down within a black hole? Yes, or that's what we think so far. We are not sure that some of these laws that we see here, they don't actually apply within the singularity of a black hole. Our key question is fermions and bosons and gluons. No, those are called exchange particles. We don't have that in our syllabus. Right, so that is it. Tomde question thakle amake bolo. If there's something that you want me to clarify, I can help.
Can an alpha particle ever actually physical returns of the universe?
Yes. Yeah.
So that's when it goes to a 180.
না, 180 টাচ না করে পারে, 180 is like আস্তে আস্তে স্লো ডাউন করে, তারপর রিভার্স করে চলে যায়। বাড়ি খায় না কোনো সময়। বাড়ি খেতে হলে you need a particle accelerator. It's a device. Hadron collider, right? ওইটা ছাড়া is not possible. Quark, anti-quark doesn't give a whole number. No, wait, actually বলি, I'm watching 3 quarks, but there's a catch, right? What was the catch? যেকোনো 3 quarks, not 3 quarks that give a whole number. Yeah, exactly. So তুমি random think the quark যদি add করো, সময় দেখতে পারবা 4/3 আসে। ওইটা তার মানে combination possible না। Okay, so the combination has to be in such a way that it's 3 quarks and they add up to give you a whole number.
Can the quarks be arranged in any way possible? Like random body,
No. যেকোনো কিছু possible, but here's the thing though. Up, down is +1, let's say. Top, bottom is also +1, right? But they're not same stability. So we hierarchy থাকে একটা, up and down is the most stable. That's why protons and neutrons আমরা easily পাই. But top, bottom, strange charm, right? These are very unstable. So their combination don't last that long.
Matter and antimatter of the same order be together in a quark. Let's say we have a charm and an anti-charm.
Okay, there's a question that I want you guys to try. So যেটা এদিকে দেখো, just এখানে দেখলেই হবে, কিছু লেখা লাগবে না. So the question is that you have your the equation represents a spontaneous radioactive decay of nucleus bismuth 212. Explain the meaning of the term spontaneous in radioactive decay. So radioactive decay is random and spontaneous, right? What does it mean by random? Yeah, and anything else?
It cannot be influenced by the external factor.
Right. So radioactive decay হচ্ছে random মানে হচ্ছে you can't predict when will they decay. You can't predict which one will decay. That's the randomness of the process, right? Our spontaneity is the fact that it can't be enforced. When you can make it happen whenever you want. Spontaneous, it just takes place, right? So you can't influence its decay. There's no physical quantity or attribute that you can change, like a catalyst or anything, to make the process faster. It just doesn't happen. Okay, ওটা ওর মতনই সারা জীবন হতে থাকবে। The conditions of the universe could be very extreme or like the other extreme, মানে খুব cold হয়ে যেতে পারে, pressure change হয়ে যেতে পারে, decay doesn't change. Okay. Right, so that's spontaneous. State the constituent particle of x. X কেমনে বের করব আমরা এখানে? So it's not that difficult, you need to do balancing. So 212 হচ্ছে 208 হয়ে যায়, so উপরে কি আসবে? 4, right? আর নিচে হচ্ছে 81 আর এটা কত আসবে? 2. So what is it? Alpha particle, right? Use conservation of mass and energy to explain the release of 6.2 MeV of energy in this reaction. Conservation of mass and energy to explain the release of 6.2 MeV. এটা একটা energy value, right? So can you tell me, এখানে ওরা বলতেছে that এই এনার্জিটা রিলিজ হচ্ছে, where is this energy coming from? Yes, so এই জিনিসটা এখানে obviously ওরা হচ্ছে ম্যাথ করতে বলেনি, বাট আমরা ম্যাথে A2 তে করি। তুমি বিসমথের ম্যাথ নিবা, ওকে? তারপর তুমি হচ্ছে I don't know what this TL is. Something, okay? So bismuth নিবা, এই other element নিবা, ওদের mass গুলোকে তোমরা হচ্ছে compare করবা। You'll notice that TL is lighter, obviously, right? But তার সাথে তুমি alpha particular mass নিবা, তখন একটা জিনিস নোটিস করবা, the mass of bismuth is not equal to the mass of this TL and alpha. But TL or alpha mass is actually less combined than bismuth. So যেটা নোটিস করা যায় that দেখবা যে there's a mass defect বলি আমরা, যে দুইটার মধ্যে massের কোনো similarity নাই, there's a gap. It's a very small gap. You might say যে এখানে তো দেখা যাচ্ছে না, এখানে 212 থেকে 208 and 24 হয়ে যাচ্ছে, where's the gap, right? I'll show you in a bit. এই যে গ্যাপটা is a missing mass, right? Mass can just disappear, but mass can disappear if it turns itself to one though energy, and that's that equivalent energy out there. Okay, 6.2 MeV jeta. So the answer is basically that the difference in the masses of the reactants, right, or the breakdown is what releases energy. Now the question is, তাহলে এখানে একটু ব্যালেন্সে মনে হচ্ছে না কিছু লস হচ্ছে, কারণ 212 4 and 28 83 2 and 81, right? তাহলে where is the loss? কেমনে বের করবা? So first of all, এই mass গুলো যেগুলো তোমরা দেখো, these are a lie. আচ্ছা, periodic table যেগুলো দেওয়া থাকে most of the times. I'm not really sure Cambridge periodic table কিরকম, but ধরো কার্বনের জন্য কি লেখে 6 and 12, right? Oxygen কি 8 and right, it's not 16. Do you know that? Yeah, it's actually a number that's a record, like, you know, an improper fraction, মানে 16.001743 এরকম, right? So আমরা যখন ম্যাথ করি নরমালি আমরা 16 দিয়ে করি, and তারপর আমাদের 16টা ধরো 11 হয়ে গেল, so আমরা 16 আর 11 এর ডিফারেন্স কি 5 আসে না, তো আমরা 5 নেই, we are happy, right? But ওই decimal places গুলো কিন্তু disappear হয়ে যায়, and those decimal places become energy here. So তোমরা যখন normal whole number নিয়ে করবা, you'll notice that they're perfect, but they're not whole numbers. There are actually decimal places out there. Our J change to energy to form hoy is actually so small that 5th, 6th, 7th decimal places show up for it, which is not in your periodic table. So therefore, তোমরা কোনোদিন math করে normally আসে না। I'll give you an example. A2 তে যখন আমরা এই mathটা করি to find that missing energy, right? আমাদেরকে যখন mass দেয় for, you know, oxygen, it's 7 decimal places. কারণ ওই 7 decimal place না নিলে তবে কোনো loss হচ্ছে না। The loss shows up where? At the 7th decimal place. So that's, you have to take very precise values, and that's when you find that there's some energy loss taking place. Okay, so obviously they don't want that, because you can see that they said just use the ideas of like, you know, conservation to explain it. But to the 6.2 টা বের করতে হতো, which we do in A2, তখন তোমাদেরকে কি করতে হবে? Take the actual values of their masses, right? And তখন দেখবা যে এই bismuthের যে massটা is actually not the same as the mass of that other element in alpha. There's a gap there, a very small mass যেটা missing, and mass can just go missing, right? So what does it get converted to? Energy, and that's the energy given off. Okay, that's actually the origin of most reactions out there that give off energy. They sacrifice a bit of mass to release the energy. Okay, calculate the energy in joules released in this reaction. So 6.2 MeV কে joules এ convert করতে হবে। So আমি তো তোমাদেরকে একটু আগে দেখালাম how to convert EV to joules, right? It's into MEV to joules. So there's this extra step there, which is what? M যেটা, right? So আমরা প্রথমে এটাকে জুলসে কনভার্ট করতে হলে কি করতে হবে? 6.2 into 10, 1.6 into 10 to the power minus 19. And এই M যেটা, right? এই M টা হচ্ছে কি হবে? 10 to the power 6. That's it. আচ্ছা, so এটা করলে যেটা আসবে, that's the answer. 1 mark.
For number B1, what do we write for 2 marks?
For 2 marks, you say that the total mass of the original nucleus and the products are not equal. And the difference in mass, so difference in mass এক mark থাকে, is released as energy due to mass energy conservation. Okay. অনেকে বলতেছে এটা অ্যান্সার লিখে দিতে, এগুলো তো will come across past papers, so I'll write it there. Just ask তোমাকে একটা heads up দিচ্ছি, like what kind of questions show up here. Okay. Our হ্যাঁ, এই ম্যাথটা একটু করো তো, বিকজ আই ফিল লাইক এই ম্যাথটা অনেকের ঝামেলা হয়। পেজ 132 তে দিস ওয়ান।
The value of electrons charge was 1.6.
Right. এই কোয়েশ্চেনগুলোর প্রবলেম হয়, স্টুডেন্টস will argue that এটা তো করিনি আমরা, but if you actually go to the bottom of it, it's something that's not part of radioactivity. What's your answer? Minus 19.
And 1.067 into 10 to the power minus 31. Is it 9,000 years?
9,000?
Yes, sir.
Hey, let me check the number. What was the number of alpha particles? What's the 1.067 in 10 to the power minus 19 alpha particle? That's like a grain of alpha particle. I'm going number যখন আসে না, they must be all whole number powers for numbers. কত আসে? 9,375. কি আসে? Okay, so the way we do this is current of 1.5 picoampere. Pico down to 10 to the minus 15, right? So if your current is 1.5 into 10 to the power minus 15 ampere, right? What does that mean? It means it's 1.5 femto Yeah, sorry. হ্যাঁ, ঠিক আছে। Minus 12 ampere. So coulomb per second. Isn't that what it means, right? So এখন if that's the amount of charge that's transferred every second, what's the number of alpha particles out there? So what's the charge of one alpha particle? One alpha particle charge হচ্ছে plus 2 into 1.6 into 10 to the power minus 19. Do you agree? Isn't that the charge of, so can you tell me what is that value? 3.2 into 10 to the power minus 19, right? So that's the charge of one alpha particle. And what's the total charge transferred in this case? 1.5 into 10 to the minus 12, right? So therefore, what's the total number of particles emitted? Very easy. Number of particles would be uparetta divided by nichetta. So that's 1.5 into 10 to the power minus 12 divided by 3.2 into 10 to the power minus 19. How much is that? 4687500 আচ্ছা যাদের ওই 9 যেটা আসছে ওটা কেমনে আসছে কি করছো তোমরা আচ্ছা টুতে খালি টু নিছিল আচ্ছা right so 4687500 there are other ways probably of doing this but you know I'm just basic unitary method দিয়ে করছি এটা আচ্ছা কি করছো আইটি তে অনেকে করতে চাও করতে পারো যে ওরা টাইম 1 সেকেন্ড নেবে তারপর কতটুকু চার্জ পাস হচ্ছে বের করবে the same thing though unitary method means that right right so সানডেতে বলি আমরা কোনটা করব পেপার গুলো তাহলে ওভাবে করে আনবা তোমাদের সানডের জন্য হচ্ছে ওই লিস্ট যেটা দিছি ওই লিস্টে ফলো করব আমি বাট there are a lot of variants out there সব variants গুলো ক্লাসে করতে গেলে we won't have enough time so তোমরা হচ্ছে p মানে পেপার 1-1 and পেপার 2-1 এই দুটো করে আনবা ওকে মার্চ 2019 March 2019 যদি না থাকে আই থিঙ্ক আছে তাহলে মে করবা ওকে বাট আই থিঙ্ক মার্চ আছে মার্চ ওই ইয়ার থেকে স্টার্ট ফেব্রুয়ারি মার্চ যেটা এফএম থাকে না আচ্ছা আচ্ছা ওয়েট তাহলে হচ্ছে মার্চ করে না বিকজ ক্লাসে ইফ ইউ ডোন্ট হ্যাভ দ্য হার্ড কপি ক্লাস করতে দিব না কিন্তু ওকে ইউ ক্যান জাস্ট শো আপ হিয়ার উইদাউট এনিথিং মে 2019 করতে হবে ওকে and if you do come without your question paper তোমাকে সব কোশ্চেন আনসার করতে হবে that's how it is okay so if you show up without your question paper unsolved তাহলে every single question তোমার কাছে যাবে and you'll have to answer if you just show up with a blank hard copy yes and solve করে দিতে হবে check